Hey everyone, I'm Ryan Brunson. I'm joined by Ryan Sullivan and Iliya Risch, and today we're going to be presenting our project, which is the ultrafast high power laser amplifier.
All right, and just a little background on some of the basics of laser amplification, or even more broadly, optical amplifiers in general. These are devices that amplify an optical signal directly, meaning that there's no conversion from an optical signal to an electrical signal. And in our case, we are using a yttrium aluminum garnet to amplify our seed beam, YAG for short. And YAG crystals are great to use in solid state laser amplification when doped with the appropriate element. The element our YAG crystal is doped with is ytterbium to match the output wavelength of the laser diodes. Our YAG crystal lasers at 1030 nanometers and has an 18 nanometer wide absorption band at 940 nanometers.
Alright, next I wanted to give you an overview of our project. Here's a picture of our amplifier in its latest iteration. On the left you can see the diode stacks and their mounts, and then the optics and the mounts associated with that. Going on next you can see the mirror array, which bounces the seed beam up to 8 times through the crystals. And then next you can see the vacuum chamber where the crystals are housed. And wanted to clarify that we did not design the vacuum chamber or the crystal array. That was part of the design that got carried over from previous iteration of this project.
The constraints of our project are as follows here. So we were given a task of building this high power ultrafast laser amplifier by utilizing 4 7.2 kilowatt laser diode stacks, and these emit at 940 nanometers. And this was to pump our ytterbium doped YAG crystal, essentially energizing the crystal so that we could send a seed beam through to amplify that. And that seed beam emits at a wavelength of 1030. And these are all, as mentioned previously, the properties of the ytterbium doping allows us to use these different wavelengths.
Okay, and then just to go over the goals for our team for the project, we were utilizing laser diode controllers that were designed for a different system. And so a decent amount of time was spent retrofitting these controllers and making adjustments so that they would work with our laser amplifier. A large portion of went to design and testing the optical path to eliminate scattering and more efficiently focus the light from the diodes onto the crystal target. A lot of work went into the design and fabrication of the lens mounts that you could see in the system overview. The goals as far as the output of the system was a 200 hertz rep rate with 2 joules per pulse. And then, as aforementioned, to modify the pre-existing controllers to operate the new higher power pulsing laser power supplies rather.
Alright, for the project background, I wanted to show you that this is the previous version of an amplifier that was put together in the Advanced Beam Lab. Major difference of the previous design is that it had only one of the diodes, whereas our new design will have 2 diodes, which changes the optical path considerably. With the previous design, we were able to use as much as 50% of the components, but much of that had to be redesigned because of the different lenses and different mounts that we had to use.
Alright, continuing on here, we're just going to delve deeper into our actual contributions to this project, because obviously with the scope of this project, we didn't do it all ourselves, and these are just going to be more so how we participated in the larger group on this project. So to start off here, just going into the mechanics, you can see here the image on the right is going to be the diode cooling holder, which has 2 primary purposes. One, obviously, to cool the diodes, and the other to put the center of the diodes at 5 inches. And this was the first kind of part that we worked on, and we went through about maybe 8 or so iterations, and really that was due to a lack of experience in the 3D modeling software and using the CNC and doing machining in general. Just a lot of what we didn't know caused problems when we actually tried to machine it. And some of the other main components that we went through and designed and machined can be seen here on the left as the lens mounts and holders, the breadboard, the diode mount, which is shown here on the right, and the dummy load. So here was a prototype we made to kind of prove a concept for the breadboard that we're designing, and it was more so to make sure that the cooling design we had made would work on our actual breadboard. The size of the breadboard is roughly 3, maybe 2.5 feet by 5 feet, so we wanted to make sure that this design was functional before we went ahead with this design. So it's really just a copper pipe and laid in sheet of aluminum with brass connectors to bring the water to the top of the board. Here's another part we designed. This is the dummy load that we used to test our controllers. The primary purpose of this was so that we had somewhere to test our controllers without testing on the actual setup. And this was just to prevent any damage to the diodes, as they are quite expensive. But all these components, we really learned a lot in terms of 3D modeling and machining.
All right, I want to take a little bit of time and talk about another large component of our project, which was retrofitting the controllers for the new power supply and the new laser amplifier system in general. I just want to include a picture here on the right. As you can see, it just shows kind of like the server rack, how we have it set up when we're testing the devices. And so you can get an idea of what they look like. And here in this image, you can see this was taken during some troubleshooting process with the interface between the diode, the laser diode controller, and the new power supply. One of the problems that we ran into is that some of the communication protocols between the new and old power supply weren't the same, so we had to take our time and go through all of the pins on the connection and observe the signal and determine what needed to be changed in the controller to make the new power supply work. Oops. And here's kind of a similar thing, and in the back corner here you can actually see the new power supply. And again, this is I think taken even the same day in the troubleshooting process here. And then here, getting a little closer on the circuit boards. On the right image, you can see how a additional circuit board was made, a breakout board as we call them, to replace some of the components on the pre-existing controllers. And this just allowed us to make it work for the new application. Again, here's another image. This is a back panel on the diode controller, and you can see how we made the edits to the board, removed some components, and add the new breakout board. So a large amount of work definitely went into retrofitting these controllers, testing, doing different iterations, and making changes to our plans and the circuit design.
Next, I want to talk to you about our contribution in the optical pad design. Here in the picture on the right, you can see our amplifier and some of the elements. The purpose of the optical path is to take the output of the laser diodes and to colorize and homogenize the beam onto a crystal target, and the spot size for that would be about 20 to 21 millimeters. This is a picture of the assembly process, and you can see on the right in this thing that looks like a lollipop, the beam fluorescing after it's being columnized and focused from the first lens. And then this is towards the end of the amplifier, you can see the hexagon shape, and then finally you can see the 2 hexagon shapes on the actual crystal target.
And some of the applications of high power laser amplifiers are as follows here. So you can do materials processing, laser lithography, and ion and particle acceleration. Although our setup in the lab is purely for research, we will not be seeing any of these applications done with our current setup.
Okay, and then we just want to cover some of the future plans for the project, because the 3 of us will be graduating and will no longer be participating, but the project itself is going to continue on. And some of the goals for the future team is going to be to increase the output power, and the rep rate rather, The output power stays the same, but up to 400 hertz for the rep rate. And potentially increase the output power. And so the plans for that is to add a third optical path. So right now it consists of like 2 lanes, 2 optical paths, and in the future they're looking at adding a third. And finally is to create the breadboard and enclosure to package the whole thing up into something that's robust and reliable, and you know, protects it from damage to the lens and things like that.
Anyways, thanks for watching our video, and let us know if you have any questions.
Yeah, thanks a bunch, guys.